we call this as the life cycle assessment, or tools for environment assessment. And basically the LCA, or it's more life cycle assessment, consider the inputs and outputs of entire production systems. As you see in the reference energy systems, we have resources or raw materials, we have energies and waste, input and output. We have also resource extractions from raw material acquisitions to final utilization or disposal of the products. So this considers a comprehensive environmental overview of the product from cradle to grave. And just here, I just put the text in red. If we say, is biofuel carbon neutral? So it's a bit difficult questions, but if we consider only tailpipe emissions, or just if what we can say, even if we say electric vehicles carbon neutral, and we need to consider the whole lifespan, whole life cycle of the product system to answer these questions. Okay, therefore, the need for entire life cycle assessment is required. And it's a tools and techniques for assessing environmental aspects of the products and services. And we have one standard ISO guidelines so that we will have uniform and coherent study for assessing environmental sustainability. And basically, we need to know how do we do LCA and why, and also how do we validate the study from the LCA, the findings. And also this helps to evaluate the different energy systems. For example, which one is better, solar power, wind power, or biomass power? Which ethanol or which biofuel option is better? Is it corn ethanol? Is it sugarcane ethanol? Is it palm oil, biodiesel, or soybean? So this LCA is basically help to analyze, compare different energy systems. Could be any kind of energy, and also could be non-energy systems such as cement productions. Okay, it's also cement production or LCA of iron and steel. These are also very carbon and energy intensive industries. Okay, and basically LCA has one standard framework divided into different 4 stages, starting from goal and scope definitions. This basically describes the object of the study and also what are the product systems and system boundary under consideration. And also we need to get the data, basically called inventory analysis. It's basically what are the material inputs and output, and also what are the environmental releases such as emissions and waste in the whole supply chain of the production systems. And then thirdly, we have impact assessment, impact at the midpoint or more, and also could be in the end point as well. So here impacts refers to human and ecological effects such as resource depletions, climate change impacts, land use, ecotoxicity, and so on and so forth, also including acidification and eutrophications. And interpretation is basically how do we interpret results? It's basically carried out to select the products and services based on envisioned environmental performance and in order to comply with the objective study. And also we have different rules and laws and regulations. And also we need to declare the products or services. Therefore, the LCA is used to also follow the standards and also eco declaration standards, and also compare the product systems so that the buyer would be familiar with the environmental impacts of the production systems. And basically, I think this I would like to skip this one maybe. And this is the one study that I was involved. We have done a LCA of cement production in Myanmar. And basically, we consider all the life cycle as mentioned, starting from raw material extractions to raw meal preparations and calcination and cement production. We consider all the material flow, all the energy flows, even considering all the waste, the emissions, environmental releases in the whole production systems. And we have performed the LCA using different 18 environmental impact categories, starting from climate change to ozone depletion to fossil fuel depletions. Okay, and basically the highlights of the study is basically calcinations accounts for calcination stage accounts for the most environmental impacts, and increasing natural gas fraction in fuel mix will likely reduce most environmental impact. So basically, they have been using coal as a fuel. If we switch to natural gas, then could help to reduce environmental impacts. But of course, if we switch to biomass, then of course it will further reduce the environmental impacts. And then how do we perform LCA? As a LCA practitioner or as a researcher in LCA, or LCA meaning the tools to assess the energy systems, okay, to assess the sustainability energy systems. So then how do we perform? Do you have any reflection or okay, then as I mentioned, we did in LCA there are 4 stages, starting from goal and scope definition, inventory analysis, impact assessment, and also interpretations. So first, we need to know what is the purpose of LCA. Now referring to energy systems, okay? Why we need LCA in that particular energy systems? Maybe batteries, storage, hydro, wind, solar, so on, okay? And who is the audience, okay? And what is the function unit? Function unit is what functions? Like maybe if electricity, then it could be kilowatt hour. If it's a cement, it may be ton cement production. If it's a biofuels, maybe megajoule. If it's a the transport system could be passenger kilometer or ton kilometer. It's depend on it's a passenger or freight transport, and how long and to what quality, and what are the system boundaries. Okay, and what data do we need? What assumptions are we making? Any limitations? And ways to reduce. These are the most important. The ways to reduce environmental impact is basically one important because it's basically identify the most important hotspots. Okay, these, because for example, the calcination states, as I have shown in the previous example, has the most environmental impacts. Okay, then we need to see what are the material energy flows in that state. Or calcination could be one just production processes, or could be energy inputs, and when our suggestion was if we could switch from coal to natural gas, could reduce environmental impact. So we need to identify the hotspots and propose ways to reduce the environmental impacts. Okay, then what conclusion can we draw from the study? Okay, and these are some of the steps or more how do we perform LCA. Okay, and also what recommendation can we make? And now basically this is more basically the original LCA has more not spatial or temporal dimension. Now we also have dynamic LCA, and also I had given a lecture on how we integrate AI in performing AI, meaning artificial intelligence, in predicting environmental impact, just linking AI and LCA. And that is also one of interested in one of my research area these days. And then there's a more life cycle model. I think it's just I have talked about that. So it's basically from the raw material acquisitions, process, transport, manufacturing, use, and also waste management. And we need to consider resources, raw materials, energy, land, that is input needed for the production system, also environmental releases such as emissions, water, and so on. And also, as I mentioned, definition of system boundary is also very important. Okay. And as you see in this slide, so we have cradle to gate, it's until we produce the product. Gate to gate, that is more operational stage. Okay. And we have cradle to grave, that is complete life cycle, starting from raw material acquisitions to process, transport, manufacturing, use, and waste management. Okay, so we need to define the boundary so that we can compare. Okay, if we have one LCA and get to get, the other LCA and cradle to get, then it's difficult to compare because the system boundary is different. Okay, so therefore we need to understand what is natural or technical systems, the basic inputs from technosphere, and also nature, and output to nature, that's basically air, water, and soil, and also technosphere, that is waste to treatment. Okay, and significant or insignificant processes, because in complex systems such as, let's say, I have done recently a LCA of dehumidification systems, and it has many components. So we need to consider also which impacts or which system boundary has a most important roles. So therefore, we define the cutoff. Maybe if the level of significance is less than 2 or 3%, then we just consider that this may not have significant impact. So therefore, we put as a cutoff ratio. Okay, and also what are the environmental significance? Also monetary values, mass, and also it depends on what are the significant processes and insignificant processes, and also geographical and spatial locations, choice of energy mix, where should data sets from, okay, and also temporal, time period, time requirements, okay. It's a long terms. For example, in landfills, we have emissions until 100 years time. So therefore, we need to also consider time span as well. And then just reflection, then why it is important. Just LCA in the system, why it is important. So it's basically product or project development and improvement, strategic planning, policy making, marketing, eco declarations, and basically we have ISO, stands for International Standard for Standardization, provides guidelines to ensure that LCA is carried out in a certain coherence, uniform, transparent way. Okay, and there are different type of LCA. I would like to skip, but I will hand over the slides to Fazal so that you can disseminate this slide to all the participants. Okay, is we have standalone LCA, we have comparative LCA, and comparative stands for compare different product systems, of course with the same functional unit. Okay, we cannot compare if the functional unit is different, because we cannot compare like kilowatt hour or gigajoule, because they are different units. Okay, so we need to compare if electricity produced from wind, solar, if the function unit is kilowatt hour, it should be kilowatt hour for all energy systems. Okay, okay, then, and consequential LCA is also very important when it comes to bioenergy systems, because this aims to describe how environmental relevant physical flow will change in response to possible decisions. Yes, and there are different environmental impact categories, and most importantly, climate change, and other listed here: ozone depletion, toxicity, one related to health impacts such as respiratory inorganics, ozone, acidifications, land use, resource depletions. Resource depletion includes minerals, fossil, and also water as well. And I think just I have taken there are different impact methods, and I have taken recipe, and also there is revised recipe methods published in 2018, and EcoInvent maintain the data. But of course, we need to pay to get the EcoInvent data. I think more than 30,000 database are available for different production systems, not only for energy, but also agriculture system as well, or other product systems. So now, having said this, I'm talking mainly on how do we perform environmental sustainability of energy systems. Okay, and sustainability doesn't only mean environmental assessment, but also we need to also consider socioeconomic, technical assessment. Okay, so now following slides, I will present a brief overview of techno-economic systems or techno-economic analysis of energy systems using waste to energy as one options for getting energy from waste. Okay, then now I will focus on techno-economic and also together with environmental analysis of technologies supporting waste to energy. So I consider here waste to energy as one example. Okay, as one energy systems. Okay, so basically when it comes to affordability, so of course we need to also consider economic aspects. Okay, whether energy systems is affordable. Okay, so basically, when it comes to bioenergy systems, we need to consider, is feedstock available? Do we need pre-treatment? What is the configurations, the size, scale, and what are the different treatment options, location, also the financing? Okay, so the cost are variables and specific to the projects. Okay, and with many waste technologies, the economic of scales matter. So I'm trying to highlight here the sustainability of energy systems, more focusing on waste to energy systems. Okay, but you can also use and the matrices used to evaluate the techno-economic performance of energy systems in other contexts as well. So here, the costs are dependent on feedstock, okay, pre-treatment, the need for pre-treatment, the configurations, output, and also locations. And we also do a lot of the supply chain optimization model, supply chain optimizations for energy systems. So where to locate the refinery or energy production unit, and based on is the resource available in the vicinity and where is the demand. Okay, if the demand is one very isolated locations and there is a production plant, then it may not be sustainable because it costs a lot of money when you transport energy from one, or let's say energy or even feedstock or resources from one source, one location to another one. So here is a more simplified flow sheet of energetic scenarios for economic assessment of this municipal solid waste utilizations. We have municipal solid waste and we have different scenarios. Scenarios basically, we have different technical options, such as waste can be sent to landfills, and where this sanitary landfills, where you can also get gas recovery that can be used to the gas can be used to produce energy, maybe electricity, or also as a transport fuel. In here in Stockholm, biogas recovered from municipal solid waste and also from municipal wastewater is used to use as a transport fuel, okay, as a biomethane. Biogas upgrade to biomethane can be used, Stockholm is using biomethane as a transport fuel. Basically, biogas derived from anaerobic digestion of municipal solid waste, and also biogas recovered from wastewater treatment plants. And we have incinerations, okay, that we just burn the waste to get electricity and heat. And heat may be important in the countries like Sweden. We need a lot of heat during winter period, okay. And also we need to also understand the cost of turbines, okay, also digesters, and how much is basically the cost for production of energy in different production technologies. And also we need to know the capex, more what is the capital cost, and also operational expenses. And capex is basically the physical asset, such as buildings, equipment, machinery, and vehicles, and opex is basically includes the operational cost, okay. That is basically the staff cost, running cost, and also costs related to the kind of operational cost, okay. Could be also related to fuel consumptions while operating the plants. And the revenues, on the other hand, so I have mentioned about the cost, capex and opex, and revenues is basically when it comes to waste to energy systems. Revenue we can obtain from gate fee, that is basically the polluter pay or more while receiving the waste. Then treatment plant will get some money. It's more from the people from the industry that will divert their waste for the treatment. So it's called gate fee, and also that is one of the revenues. And another is digester cells. Maybe in anaerobic digestion plants, we have biofertilizer or biodigested that can be sold as a fertilizer. That is also one source of revenue. Then we have electricity and heat cells. And then other social income such as incentives, grants, and also some sort of feed-in tariff, different policies could also help to generate revenues. And gate fee is basically, as I said, waste producer pay a gate fee for ADC is anaerobic digestion facility for accepting or treating their waste. And digester is as a fertilizer or soil improver, and also it's generating a source of income. And biomethane is basically as a natural gas alternative for gas injections, or as can be used as a transport fuel as well. So then the environmental issues are more related to reducing the fossil fuel, diverting waste from landfills, reducing GH emissions, and also reducing pathogens, and also this anaerobic digestion, or one of the waste to energy options, can also reduce odor intensity of the waste. And there are other aspects that also we need to consider when it comes to sustainability of the energy systems. Here, more on waste to energy systems, we also need to understand feedstock producers, farmers, food manufacturers, local authorities and municipalities, landowners, local municipality, more this on social aspects. Also, we need to consider in designing the sustainability of energy systems. Energy companies, heat user, if we produce energy, then if there is no user, then of course project would not fly, or would have, we can not say that it's a feasible project. So we need to also consider the entrepreneurship, also investors, that includes banks or private investor. If the project is feasible but there is no investor, then of course the project cannot be operational, or cannot be, we may not have investments on the even sustainable projects or energy projects. So and there are some of the matrices used to perform economic analysis, and this is called time value of money, present values, rates, basically interest rates, interest formulas, net present values, internal rate of returns, and also payback period. These are some of the economic parameters used to evaluate the economic or financial viability of the energy projects. And basically, I think you may have heard about what is time value of money. It's basically a dollar is worth more today than it is tomorrow, right? That's called time value of money. And this is called known as the time value of money. And of course, we need to also use what is the discount rate. And there are different cash flows. Also, you can find Excel sheets. And also these days, Python or MATLAB courses are available to even make these cash flows, okay, or discounted cash flows. And also we can measure the present value by using discount factors, okay. And I think that's I think you perhaps know about this this discount factor, and how do we calculate time value of money, just considering the worthiness of the value of the money, and it is more worth today than it is tomorrow. Okay, that is what we call. And also discount rate adjusts the time value of the money, and also I also consider the systemic risks associated with the financial viability of the project. And this is some of the formulas. I think you may have seen this, and this is the way how do we calculate the net present values of the projects, of any energy projects, okay, using the discount rate of maybe it could be 6%, it could be 8%, it depends on where the project is located, okay. And another metrics, as I said, is NPV. NPV is one of the most important matrices for evaluating the sustainability of projects in more economic sustainability, okay, or financial sustainability of the projects, okay. So I just present these formulas, and you know how to calculate, okay. Then also use levelized cost of electricity, as one of the matrices to evaluate which energy systems is better. For example, solar, wind, biopower, hydro, or nuclear, or other electricity generation options. Okay, and here just one statement here: if the energy cell tariff is higher than levelized cost of electricity, then the proposal is, we say, economically viable. Okay, and also it's more presentation in diagrams about how to calculate NPVs. And also we also do cost benefit analysis, and this is a conceptual framework. And that's also it includes all the matrices or economic parameter as mentioned previously. And basically internal rate of return, the net present values, cost benefit ratio, and also payback period are used to assess the financial viability of any energy projects, okay, or sustainability of energy projects. And this IRR, or internal rate of returns, refers to discount rate, which makes the NPV of the cash flow equal 0. Okay, and there are some of the decisions that we should follow. Is basically a net present value. A project with a positive NPV is worth investing in. Okay, that is one of the decision rule when estimating the financial viability of the projects. And here basically it shows how NPV is considered the decision rule, except a project which has 0 or positive NPV. Alternatively, use NPV to choose the best among the set of mutually exclusive alternative projects. Okay, and also we perform also sensitivity analysis, okay, on different interest rate, and also investment rule is accept a project with IRR larger than interest rate. Okay, these are some of the if you like to really perform economic viability of the projects, then of course IRR could be one of the matrices, and also most importantly NPV. Okay, NPV should be greater than 0. And this is the one of the paper that it's under review. We have done different scenarios of the waste to energy options. We consider land use options, landfill, landfill, like waste to be sent to landfills, and waste to be sent to the incineration plant, waste to be sent to AD or energy digestions. And we have done techno-economic, also including environmental aspects, for exploring which options is suitable. And also we consider the different policy targets and also different scenarios, and so as to get the optimal technology selections, and also considering the temporal and also spatial dimension of the waste to energy system. And considering one city in Brazil, that was one of our projects funded by farmers, and hopefully the project paper will be available online soon. And I will definitely share how do we did this analysis. Okay, and maybe this is also very important to understand business model. Okay, because without business we cannot afford projects, right? So there are different approaches to develop business in the energy systems. Here, more focusing on waste to energy systems. And there are different stages, starting from what are the key activities, key resources, and value propositions, partnerships, customer relationship. It basically comes from business, but can be used in different energy systems as well. More on how business can be created, developed in the energy systems, looking into waste to energy here. Okay, and then now I think this almost, I'm just nearing to my presentation. So just I would like to ask if you have any questions until now, especially on techno-economic analysis of energy systems, but with the examples waste to energy, but that can be applied in other energy projects as well. And here is the questions for you. So what are the challenges? And in the pathways, we have different pathways. We have different energy systems to meet our energy demands. So what are the key challenges to net zero? Net zero is basically net zero emissions. We have carbon intensive energy mix. That is very challenging, right? To decarbonize or to pathways to net zero. Second challenge is there is a social conflict on renewable energy in different development contexts. Whether to go for solar, wind, and also societal aspects, okay? And if as you see, when we plan to develop hydropowers in developing countries, there are a lot of the environment assessment need, and also, of course, I'm not saying that there is social conflict there, but these are some of the challenges as well. We need to also understand the societal need and also societal social conflict, the investment, and low public acceptance, coal financing still, and carbon intensive industries. I think I would say, would like to add on the list the other challenges in the pathways for decarbonizing the energy systems. Some of the solutions here is basically decarbonization of power sector could be put on priority, phasing out coal, more renewables, and of course, investment in more renewables and more storage to overcome the limitation of this power, the shortage portfolio, and also engagement of major industries, and also leadership not fully understood the climate associates, and also opportunity on business. So it's also very important to convince the policymakers about the severity of the climate associated risks and also opportunity on business. And also we have the financing options, and green financing, carbon financing, also government support needed. And also we have novel technologies such as hydrogen, CCC, BECS, bioenergy, capture and storage, and also other R&D work going on the, let's say, electric fuel as well, e-fuel. And also just here, the opportunities are there. And this is basically the cost of renewables dropped drastically, and it's also, as you see, the solar PV economically competitive with other fossil fuel generating units, okay? And now new renewables beat existing coal plants on operating cost, okay? And these are the, I would say, more opportunities, okay? And as you see, majority of renewables undercut cheapest fossil fuel on cost, okay? And this is opportunity of more.